So this video is going to discuss creating vectors in Matlab and Octave. So I'm going to give a few definitions, and then I'm just going to show you lots of different ways that you can create and manipulate vectors. So let's start off with a scalar. A scalar is not a vector. A scalar is just one value. An array is kind of a general term that is a group of numerical values that could either be a vector or could be a matrix. So in general, for computer programming and stuff, they use terms array, but in mathematical terms it's really normally considered a matrix. So a vector is a single line of multiple values. It could be just two values, or it could be dozens of values, or thousands of values, or millions of values. A row vector is a horizontal row of values, and a column vector is a vertical row of values. And you can actually transpose those using a hyphen, and I'll show you that. So a matrix is multiple rows and columns combined into one variable or one element, considered a matrix. And again, sometimes that's considered an array, depending on kind of who you're talking to, I guess, but I'll use the term matrix most of the time. Now when we have an array, vector, or matrix, and we want to select an element within, or a group of elements within that, then we need to know the indexes of those points. So we'll look at the indexes, and we'll look at how we can extract indexes and how we can manipulate indexes. Alright, so if you want the very first value within a vector, that would be index 1. Alright, a lot of computer programs try to index an array starting at 0, but the Matlab and the Octave software index the very first value of an array as 1, not 0. So it starts counting from a 1. And so that can be confusing sometimes, especially because we'll typically be using a time vector as our independent vector. And time, usually we want to start time at time 0 at the beginning of the simulation or of the occurrence in there. So t parenthesis 1 would indicate that we're getting the first element, which if it's a time vector, it's most likely time equals 0. If you want the second element, then you would put in a 2. If you want the fifth element, you would put in a 5. If you want the last element in the vector, you can put the number of the last element if you know what it is, but it's there's a built-in kind of variable called end, which will get you that very last value. Now if you want the next to last value, you can do something like end minus 1. If you want the second to last, you can do end minus 2. So this allows us to manipulate and pull those values and not have to worry about exactly how long that vector is or how many elements are within that vector or values. Okay, so when I say element, I'm referring to one value within the vector. Alright, we can also grab a range of vectors. We can use a notation like 2:5 to grab elements, the second element, the third element, the fourth element, fifth element, and I had the sixth here. I was going to do the sixth like below. 2:5 is just going to get 2, 3, 4, and 5. It would not get the sixth value. Alright, and then 2, 2, and 6. Alright, so I updated that slide there. So 2:6 will give you the second, third, fourth, fifth, and sixth values within the vector. We can also kind of select and skip some of them. So we can give a range or a vector of indexes to select various different indexes. So like 2, 2, 2:2 2:6 would grab the second, the fourth, and the sixth values, but not the third and the fifth values. Alright, so given that information here, let's just go over and start doing some examples here. So I'm going to be using the Octave software today, and so this is just running on my local computer, and again, everything that we're doing here you can do in Octave or you can do in Matlab. There's just a few nuances every once in a while that you get into in the different programs, but the Octave program is a free, what they call open source program that you can download. It'll run on a Mac, it'll run on Windows, it runs on Raspberry Pis if you have a Raspberry Pi computer, if you know what that is. Alright, so as you can see here, it looks very similar to the Matlab Layout. We have over here our file browser window. We have our current directory up top. We also have like editor windows and those sorts of things. And we have our workspace telling us what variables we have, and of course our command window. Now, as you can see, I had some stuff in here. So the first thing I want to do is just remind you that you can clear, if you type clear, clear wipes out all the variables that you may have already created so that you start from scratch. I highly recommend that you always start your scripts by clearing out all your variables and clearing out all your figures. That way when you rerun the script, you're not, if you have something in your script that is wasn't updating, so you manually created a variable or something, or it would you would end up getting an error as opposed to having it run the code with old data and you're like, why is this happening? So the other thing is we can clear the command window. So I'm going to type CLC to clear command window. So clear will clear variables. Now if you have a lot of variables, let's just create like A is equal to 1, B is equal to 2, A2 is equal to 3, A4 is equal to 3.14777. Alright, so that's not pi, that's just a number there. Now notice these are all scalar values. So one of the nice things about viewing the workspace here is we can see these are a 1-by-1 array, which means that it's a scalar. We can also use the whos command to view these at any given time. So I have like A, A2, A4, and AB. I think I said A3, but I must have hit the 4 button there. Alright, so the A2, A3, A4, A2, excuse me, A, A2, and A4, and B. Now, with the clear button, I can just clear one. So if I just like clear A, clear space A, oops, I cleared them all. Recreate them here. Alright, so try this again. Clear, okay, A is equal to, alright, I hit the up arrow key, which recalled some text that I had. A is equal to 1, A2 is equal to 22, A4 is equal to 44, B is equal to 12, B is equal to 12. Alright, so we can see there's those variables again with different values in them. But now if I type clear A, it will delete just that one variable. So we can clear just a single variable. Or I could type something like A star, which would clear all variables that began with A. So if the original A would have still been in there, it would have cleared that also. Another thing is, right now I've got this variable B, which is a 1-by-1, which as I said is a scalar. But if I type, if I was to type in here A is equal to bracket, or excuse me, B is equal to bracket 1, 2, 3, this is going to create B as a vector. This is going to be a row vector, so it's 1 by 3, so there's 3 elements. So it's a row vector, but this row vector has 3 elements. So notice that it totally overwrote the B that was there before. So you kind of have to be careful here. You can overwrite variables, you can overwrite values that are in there before, that were already in there. You can just totally overwrite them and make them something completely different. So it's not even a scalar anymore. B started out, it was a scalar. When I said B is equal to 12 up here, B was a scalar. But now I said B is equal to bracket 1, 2, 3, and so now all of a sudden B is a row vector with 3 elements. Okay. I can then overwrite B again and set it equal to pi. Now pi is a built-in variable that is a very precise version of pi. So remember that, you know, pi is this irrational number that just kind of goes and goes and goes. But so it shows you here that B is 3.1416. But in reality, if I simply change my format, I can look at that. B has much more accuracy than just 3.1416. So the value of B is actually 3.141592653589793. So it's very, very high precision value of pi, much better than just saying 3.14 or even 3.1416. All right, but now notice though, when I did that, I created B equal to pi, so B is now a scalar again with just one value in it. So it was a vector with multiple values. Now all of a sudden it's down to a scalar again with just a single value. Alright, so let's go ahead. I'm going to clear again, clear all my variables and kind of start again. So if you just do a calculation, you know, something as simple as like 3 plus 4, all right, what happens is that Octave and or Matlab will store the result of that calculation into a kind of default variable called answer, ANS. And so in this case, ANS is simply a scalar, because I did a scalar calculation. But if you were doing some sort of vector calculations, then ANS could be a scalar. But this is a valid variable now in the system. As you can see, it's actually defined over here. And so now that once it's defined, you can use it for other calculations. So we can say something like, well, answer now is answer plus 3, and so now answer all of a sudden has the new value of 7, which was the old value, plus 3 more, which of course is 10. So we can you know, so it's if you don't assign a variable when you do a calculation, it's going to automatically store it within this answer variable. And you can use the answer variable, but just be aware that, you know, the next time you don't assign it into a variable, it's going to get overwritten with the new value again. So it's much better to create variables that for your vectors and stuff, and not use the ANS, the built-in answer one, because it's going to change every time you use it. So if you ever want to go back and recall that variable, you need to do that right away. Alright, so the simplest way to create, I'll clear this out again. So the simplest way to create a variable is just simply, or a vector, is simply say something like B is equal to, as I said before, 1, comma 2, comma 3. Now notice, just to kind of show you here, the spaces really have nothing to do with that. However, you can actually declare this as a row vector by not using commas at all, but just putting spaces in between them, and you can make it a vector. So both of these were row vectors here created. This one I had commas. I recommend that you put the commas in there with or without spaces around it. It's fine, but I recommend that you use commas, because sometimes if you're trying to use spaces, the spaces get deleted and then you're one short. So if I tried to like recall this and I do 49 and 33 now, it went from a 1 by 3 vector to a 1 by 2 vector. So I recommend that you put the commas in there, but they're not actually needed. We can also make a column vector. If I do, we'll call this one C. I can do a column vector, and the column vector then is we can do it without symbols by simply hitting the enter key. So I can do 1, enter 2, enter 3, and then put my closing bracket. And so now you can see this is a 3 by 1 column vector. And so it's going down vertically as opposed to across horizontally. So this is a row vector. This is a column vector. Now the preferred way of doing column vectors is to use semicolons to give the next column. Okay, and to put semicolons there and make it a column vector. And then when you're doing arrays now, so if we wanted to do an array or a matrix, we can mix, and so we can have I'm going to do 2 columns, so it would be 1 comma 2 semicolon the next row 4 comma 5 semicolon the next row 9 comma 8. Okay. And so now when we perform this, then right, we can see that A is a 3 by 2, so it has 3 rows and 2 columns. 149 is the first column and 258 is the second column. Now I can also create a vector by pulling data out of an existing vector. So remember up here we had like C had 23 and had 1, 23, 44, and 55. So if I created C1 and I say in C1 I want to pull out, actually I'm going to call it 23. So C23. Now notice when you create variables, you can use underscores if you want, but you can't use a hyphen, because if you use a hyphen it's going to do subtraction. So let's look at that before I'll get back to pulling the data out. If I do C minus 23, I get my answer variable. And my answer variable, what this did was this subtracted 23 from each individual element. So the first element in C was 1, so I subtract 23, I get minus 22. The second one was 23, so I subtract that, and of course I get 0. 23 minus 23 is 0. The next one was 44, I subtract 23, I get 21, and 55 minus 23 is 32. So notice I get the answer because I didn't assign it to anything. I just said C minus 23, so I got my answer variable. My answer variable is the same size as the C vector was, but all the values had 23, are 23 subtracted from the values within the C vector. All right. So so you can't use hyphens for a variable name because it's actually going to try to do subtraction at that point, or will if it's valid subtraction instruction, it'll do that. And what I mean by that is if you're trying to subtract a row vector from a matrix or something, or a row vector from a column vector, that would not be a valid calculation, and it would actually give you an error. So like if we tried to take C, which is a 4 by 1, and subtract B, okay, well, it actually did do that. Okay, so it did do that, and it gave me an answer which is a 4 by 2. Okay, so but there's certain types of calculations and stuff are not valid. So you know, like when you're doing vector multiplication and things like that, you have to be careful because some things would not be done correctly on there. So, but notice, I mean, I subtracted C from B, and it actually ended up with a 4 by 2 matrix. Alright, so but let's go back up here to the C matrix, and I want to pull out the 23 and 44 and put it in a variable called C23. And so what I'm going to do is I'm going to say grab the C vector, parentheses, and get the second and the third element out of that. Alright, and so you can see now I get a new vector, C23, which is made up of the two of the second and the third elements within the original C row vector. All right. Or yeah, the original C, it was a column vector. These are semicolons, so it was a column vector. So I got so I end up with a column vector of just those two elements. Now on the other hand, if we look at the B, now if you anytime you want to view some variable, you can just type that variable again to see it because it was lost way up there. So we have B is made up of these two elements. So I want to get B end, for instance. I can say B end and pull out just the last element. Okay. Or I could do, as I showed, B end minus 1. So I might do something like this. B end minus 1 is going to be n minus 1, which of course in this case is actually the first element of B, but in the longer elements it would just be the next to last element within there. Now when we want to create longer vectors, there's several different ways that we can do that. Number one, if we just wanted you know, like a lot of times we'll be creating an independent variable t which we want to have as a certain length. So we could do we could say give me t 0 colon 12. I'll just do 12 of them so they'll at least show up on the screen and not wrap around. Alright, so t 0 colon 12 gives me a row vector of these 12 elements. Now notice here I didn't put brackets around here because I'm using this like step notation. I can put the brackets around. It's perfectly valid either way. Now normally when we're going to do this, we're going to put on the semicolon so it doesn't display those values. I mean, in this case there's only 12, so it's just one row, so it's not that big of a deal. But if there was 100 or 1,000 elements in there, then we get lots of numbers in there. So using the semicolon just suppresses the output of that value. Alright, so but using the this colon notation, we can get a range of values, which I had kind of demonstrated up here, 2 colon 3. But just I just want to talk about here. Notice that the index is stepping by 1. So we're going from 0 to 1 to 2 to 3 up to 12. Okay. Now if I came in here and I said well, before we do that, let's look at the size of this. Remember, we can look over here and see here's the size of t and it's 13, or we can type who's t and we can see the size of it. So even if you have this workspace window hidden or closed, you can always use the who's command to see the size of your variables. Now I wanted to point out here, right, I said I want t, and the last value of t is 12, but when we look at the size of it, we get 13 because I started t at 0. So the first element of t is 0. The second element of t is 1, right? The last element of t is 12. The next to last element of t, of course, is 11. So notice it's stepping up by 1. So we get an even step in time from 0 to 12, because I said go from 0 to 12 and the steps are nice and even, stepping by 1. Now if we want a different step, then we can add that in the colon notation. So I can come over here and I can have my start value, which is 0. I can have the end value, but in between those then I could put the step. So I could have the step here, and I can make the step say 1/2. All right, and let me take the colon away. Now when you see here, now I still have this long format. I forgot about that. So we can go back to short format. All right, and I can rerun this and view it, and so now it just fits on a few rows instead of displaying the highly accurate. Now remember, even though like this value is 0.5, right, it's 0.5 out to like 20 decimal places. Even the long format's not showing the complete accuracy of these. These are all double. If we slide this over, we can see these are all considered double precision variables. So they're very, very accurate calculations. They're 64-bit double precision values being stored in here. So it's very high accuracy. Okay, sometimes you may need even higher accuracy than that, but usually that's considered very good. It's 64-bit. Computers are 64-bit now, and so you're getting this very high accuracy of numeric calculations anytime you do this. So, but anyhow, so when we see this, right, now we're stepping 0.5 up to 12. So if we look at the size of t now, it's 25, right? So because again we're starting at 0 and we're going to 12, but in steps of 0.5, so we got 0.5 and 1, right, and so forth. That's 24. But then we got to remember we started at 0, so we have this 1 extra value. So you always kind of have to keep that in mind, that we have that 1 extra value. Now and again, these are linearly spaced because the step was 1/2. So these are linearly spaced, and I end up with 25 values. Now there is a Lin Space command. So if we do a Lin Space, so I could say something like t is equal to Lin Space, and I could give it my starting value of 0 and my ending value of 12, and I could say give me 24 of those. Now this is going to give me exactly 24 values. I'm going to call this t underscore ls for linear space. Okay, and so when we see this now, notice I only have 24 values, and each value is linearly spaced, but because I started at 0 and I only get in 24 values, these are not nice rounded values. We get 0.52174, we get 1.048, and so forth. So when you do linear spacing, if you use the Lin Space command, you get linear spacing, but you can get exactly 24 values or however many values you want. So you do have linear spacing, but that linear spacing is different than what you might expect, okay, because I wanted the steps to be 0.5 and my steps are actually 0.52, and we can see that if we take like t underscore ls, the third value, minus t underscore ls, the second value, we can see that the spacing, right, for any of these, we can also look at like the 24th value and the 23rd value, and we can see that that spacing is 0.52174. So we are getting even spacing between each of these elements, but that linear spacing is not like a fixed value of 0.5 that maybe we expected it to be. All right. There's also a log space option. So we can say T, I'll just call this log space here. Okay, and so I can create a log space. But if you remember, logarithms are based on exponents. So if I wanted to try to do a log space between like 1 to 12, now remember, if you do like a exponent, if you tried to like take the log of 0, you would actually end up getting an error, right? So when we look at this, I'm going to say log space. If I wanted to go 0, this would actually be 10 to the 1, and then I want to go to 10. I would put in the 10 here, and let's just say give me 12 values of those. All right, and so notice here we're going from 10 to the 0, right? This is 10 caret to the 0th power. All right, so this here is the power. So it's 10 to the 0 is the power, so we get a 1. And then I'm going to 10 to the power 1, which is giving me 10. So my values are going from 1 to 10, and I asked for 12 values. So I'm getting a log spacing of those values. Okay, so it's not linear, this is log spaced. But this is another way that we can do it. So if you're working with a lot of times, like if you're doing filtering or anything that is spanning several decades of values, you would want to use the log space as opposed to the linear space. So notice here I'm going from 1 to 10, but I have 12 values in between there, but they're spaced based on a log scale. So these are built-in functions. The Lin Space and the log space are both built-in functions that allow us to build up vectors, and we can just say how many points do we want, and you can tell it 12 points or 100 points or 1,000 points, and get those values then. Right? Some other built-in functions are like the zeros. Let's say that you wanted a vector z, which is all zeros. You can say give me zeros, and you can say I want a row vector with 6 elements. All right, so you got to tell it how you always got to have at least one row here. I put in 0 there. I had 0 in my mind, so I'm putting in 0. So you got to have like one row and 6 columns. I was like saying, give me 0 rows, and that's exactly what it was doing. It's giving me 0 rows, like I asked for. But or we can make it a column vector with 6 elements by putting 6 rows, 1 column, right? So this one here is 1 row, 6 columns. This is 6 rows, 1 column. So this is the column vector, this is the row vector. Or we can use the ones. There's a ones that will just give you all ones. There is a random function which will just generate random values. Now notice these random values are always going to be between 0 and 1. So you're getting some kind of random number that is generated between 0 and 1. So it'll never really be 1, and it'll never be 0, but could be theoretically any number in between those. So let's say that you wanted a random number between 1 and 10. Now, so if I take this z, and notice if I run it again, I'm going to get completely different random numbers, right? So these are completely different. Every time you run this, you're going to end up with completely different random values. So if you use this rand function in your simulation, for instance, every time you run it, it's going to generate some different values. Now, technically, this is a computer, and computer are deterministic things. So these values are not totally random. So you could actually set a seed, and when you set a seed, if you set the seed to a known value, and then you run the random function, it's actually a pseudo-random, so that those values actually will be the same based on the same seed. So just be aware of that. Computers are not truly random. This is a deterministic function, and it generates the random values based on, they use the computers actually, what they do for random values is they generate some seed values based on random things, like when, time between keystrokes. So when you hit, the 1 and then I hit the 2 key on the keyboard, how long was that? It could have been, 458.7 microseconds. But now when I hit, the 3, that one, that was more like, 2.6 seconds. And so they store these different seed values based on random occurrences or external influences into the computer, like keyboard and mouse strokes and things like that, and they generate these random numbers to help make sure that these random values at least seem random, but they actually do have some deterministic ability to them. Alright, so this random number here, or these random values, let's say I wanted to get these between 1 and 10. Well, I could say z is equal to this random, and then multiply this times 10. Alright, and so now I've got values between 0 and 10, but 10 will never be a valid option here. Alright, and so what I could do then is I could round this, so I can use the rounding function to round this, but again I'll never have, well, I guess I did get 10 because it rounded, like if I had something like 9.9, it did round that. Okay, so by rounding it, then I can get 10. But you also have to be careful because I may end up with a 0, because if it rounds, I may have to do this a lot of, oh no, right there. Just one more time, if I do the random, there I got a random of 0. So this is not a value between 1 and 10. It's a value between 0 and 10. By doing this. So you need to be aware of these sort of nuances. Now, one thing that we could do, notice again here, z, right now z is an integer value because I've rounded it, and this one is a 0. So what we could do is I could say, well, here's my vector z. Here's my vector z, and it's got a 0 in it. And so what I want to do is I want to find all the zeros. So let's take and get the index. Using the find command, I can say let's find all of z values, all the z values that are exactly equal to 0. Now notice here when I'm using two equal signs, see up here I'm using one equal sign. One equal sign assigns it, so it takes whatever this does and stores it in this variable. This double equal sign is saying let's compare. So it's very important to understand that a single equal sign is an assignment. Two equal signs are used when you want to do a comparison. So what I'm doing is I'm saying, hey, here is z and it has all these lovely elements in it. And I'm saying find me the indexes into Z where Z is equal to 0, and we find that the only match there is element number 2. Okay. Or I could say find all the Z's that are not equal to 0. Okay. And this varies depending on programming language. It's for Octave, it should actually be not equal to 0. So the bang here is saying not equal. So I'm saying find me the indexes into Z that are not equal to 0. So now I'm going to create Z2, which is equal to Z based on this index, based on these indexes, which are not including the 2 because the 2 is 0. And so now I've got Z2, which is 7, 9, 2, 7, and 3. It's all the elements that are non-zero within the original Z vector. Okay? And so these are different ways we can use this find command to find matches and pull out those values. Another thing I could do with the find command is I could say, let's find everything that is less than, remember on my original Z, I got a 7, a 0, a 9, a 2, a 7, and a 3. So let's just say everything less than 5. So find everything in Z that is less than 5. And so we find, well, that the original Z, remember you can type it anytime you need to kind of just view it. So the original Z, we had 2, the value 2 was less than 5, value 4 was less than 5, and value 6 was less than 5. So again, I could create like a Z less than 5. Okay. Notice I can't use as a variable name like a less than sign. That's not valid. Okay. The only thing valid for variable names are letters, underscores, and numbers. Okay, but you shouldn't start a variable with a number. It should always start with a letter. You could start it with an underscore, but I wouldn't recommend it. But I'm saying Z less than 5 is equal to Z, and then the indexes out of my find command. And so I can pull variables out of a vector using these this index here, and I can just kind of pull those out of there. Alright, so let's take a look. We can also create vectors based on other vectors. So if we go back and we say, here's my T, I'm going to run 0. T is going to run from 0. Oh, one more thing before I show you this is Z less than 5. Remember, you can just type the variable name to view what it is. This is a column vector. If I put a apostrophe here, that will flip the matrix. So if it's a column vector, it makes it a row vector. If it's a row vector, it makes it a column vector. And so anytime you need to do that, you can always just do a hyphen. So if you were expecting a row vector, but you, for whatever reason, have a column vector, you can just use a hyphen, and that will flip it. Or technically, the term there is transpose. It will transpose a column vector to a row vector, or vice versa. If you have a matrix, let's just go back and say we have the matrix 1, 2, 3, sem 4, 5, 6. Alright, and so if I have this, it's 2 rows, 3 columns, but if I transpose it, I get a different matrix, which is 2 columns and 3 rows, or 3 rows, 2 columns. Okay, so the transpose, the hyphen or apostrophe, excuse me, not a hyphen, but the apostrophe, it will transpose a matrix or transpose a column vector to row vector, and back and forth, so if you need that. Alright, so let's just go ahead. I'm going to clear everything again. Just clear the screen and start again. So we're going to create a time vector 0, 0.2 colon 2 times pi. So this vector is going to go from 0 to 6.2. So remember, 2 times pi, of course, is 6.283. But I'm stepping by, my time step is 0.2, so I'm stepping by 0.2. Now a lot of times when we're going to need this time step, so a lot of times I create like a TS, capital TS variable, and I set my time step using this variable. So then when I create this T matrix, then I would use this something like T is equal to 0, and then TS is the time step, because once it's a variable we can use it in there. All right, and so we can create that. All right, so so here is a time vector from 0 to 2 pi, or as close to 2 pi as we can get with time steps of 0.2. All right, and so now I'm going to create my sine. I'm going to say y is equal to the sine of t. All right, and so we can, we can see that there, and that's 32 values for our time step. And then of course we can plot that, so we can plot t comma y underscore sine, and I'm going to make that blue. Technically the default is blue, but I just always like to force the color there. And so then when we see that, right, we get our plot from 0. Now when you look at that though, you see up here it looks kind of choppy. You see how choppy that is, because my time step is only 0.2, so this line, it's going from here to here. It looks kind of because the plot command, if you come over and you put well, remember there's a help. Okay, let's look at the help for the plot command here for a minute. So when you look at the help for the plot, you can have it put in markers. Okay, and so the markers, there's a lot of different markers that are available here. If we scroll up, we can use like a plus sign would give us kind of a crosshair or plus signs at every point. O would give us a circle. The asterisk gives us a star. A period just gives you a point. The X would give you a cross, so you can get a square, a diamond, and triangles of all different angles, and a pentagram and a hexagram. So these are all the different markers that we can use, and then we can get either solid lines, dashed lines, dotted lines, or dash dot lines to kind of mark these different values here. Now and then we can use different colors. So the base colors are black, red, green, blue, yellow, magenta, cyan, and white. Now of course if you made it white and your background's white, it's not going to be very practical, of course. So, but anyhow, so when we look at this graph, I just plotted it by default, and it plotted the line. But if I come in here and I plot, and I put in, say, an O, and then it'll just give me the points on the plot. All right. Or if I do O and a dash, it'll give me the point and also draw the lines. But I want to illustrate here, right? It's drawing a line from these points. And so that's why some of these lines look, they look choppy, because they're just a straight line from each of the individual points. So really what you want to do when you create your time vector, you know, if I created my time vector even smaller, remember you can just like hit your like a letter T and hit the up arrow to recall this. But what I'm going to do is I'm going to set my time step here to 0.7. which is kind of an odd time step for this, but just put in there. So we're going 0.7, 1.4, 2.1. So notice the last value is actually 5.6 now. And then I'm going to recreate my Y. So I hit Y up arrow to recall that command, and that gives me my 8 values for the sine function. And then I'm going to hit P and hit the up arrow key and recall my plot and plot those. And so when we look at this now, again, you can see it's just from each point, it's just drawing one of those lines. It's just pulling one line there. Now, but we're plotting, the O's are indicating where the actual points are, and then the lines are just being drawn from point to point. So now, if I create T high res, so I'm going to create like a time step underscore high res, and I'm going to make that 0.01. And then I'm going to do my T, but I'm going to make this a high resolution T using the high res TS time step. All right. And so now you can see there's 629 of these. So let's just notice the last value then is 6.28. So let's do a whose T star, and you can see there's T, which is only 9 elements, and then there's T star, which says 629 elements. So now if I wanted to plot, okay, what I can plot is I can plot the T, which is the low res, and I'm just going to plot those points, and then I'm going to plot T high res, and T, or not T, but Y high res. Oh, I didn't redefine my who's T, comma, and I'm going to look at the Y's too. So I forgot to rename my Y, so I'm going to recall this, or I guess I didn't actually even create it yet. So I need to create Y sine high res using the T high res. Okay, so there's 629. So again, use the whose command, or we can look over here. But the thing I like about the whose command is you can have it just show you the variables you're interested in, where over here in the workspace you see all the variables that are there. So I just want to see the T, and the T high res are 9 and 629, and then now I have a Y sine, and then a sine underscore high res. All right, and then we can call that blue, but I'm just going to leave it there. So now I plot both of those together, and so you can see that it plotted just those points. So the O's were plotted the points at the low res, but now I still have a nice smooth curve. So I have a nice smooth curve here of the, because there's 629 points in the line, so they're much closer together. Now you don't really want to, let me put triangles in there just to kind of show you. You really don't, when you have 600 of those, if you put like a point in a marker in there, if you do it as a marker, then now you get this really kind of thick line, which I don't, sometimes you might want that, but usually you don't want that because it's just way too busy and way too thick to see values very accurately. Now when you're plotting, remember you can also use the grid command if you want to have some grid lines on there. All right, so but normally what we want to do is, again, we just want to plot a line for the high res, but then we might want to have some markers in there. But if you, in this case, I already kind of had those markers there, but let's say that you wanted to pull out, say, let's look, right, we have 629 values out of this. So let's say that I wanted to pull out 20 values. Okay, so I wanted to pull out 20 values out of that. So I could say, let's just, you know, if you divide 629 by 20, right, you have like 31. So we need steps of 31. So I could say something like, let's use a T marker to pick out, and I'm going to pick out like 20. I'm going to pick out like 20 points out of this 629. And so what I'm going to do is I'm just going to choose a marker. Now, remember, indexes have to be integers. And so what I'm going to do is I'm going to pick out of my T, my high-res T, I'm going to pick out indexes from 1 to 629 in steps of 31. Okay. And so what I'm grabbing steps of 31 because they have to be nice, even integer values. And so I'm pulling those out of here. So now notice I actually am ending up with 21 values because, again, we started at 0. So I ended up with 21 values, not 20. But I've got 21 values that are being stepped about by 0.31 steps. And I'm just going to use those now for markers. So now I'm going to do a Y marker, which is a sign using the T marker values. Okay, and so I'm going to end up with 21 values. And the idea here is that I want to create marker points in here. So I'm going to hold my current figure. So I'm going to hold my current plot, and then I'm going to plot these markers. So I'm going to use T underscore marker, and then Y underscore marker, and so I'm going to plot 21 points just using marker values. And I'm going to make these red and a star just to make them show up because I already have the other stuff. I don't know why I put hyphens around the marker. This is a variable, not a string. When you put not hyphens, I said hyphens again, single quotes. When you use single quotes, like here, this is because you're choosing strings. So when you have matching quotes, this is a string in between there. Remember, a single quote by itself, or apostrophe, will transpose a matrix. But when you have two of them together, what you can do then is grab a string. And so now I'm going to plot that then, and now you can see the red asterisks are from the marker values. And so when you have lots and lots of points, so I have lots and lots of points, like 629 points, and then you want to kind of mark just a few of those points, you can pull out some of those. So you can pull out some of those and then basically generate or execute the function using a subset of those. Okay. Now another way that I could have done that, though, instead of re-executing the function, I already had Y as a high-res value. So what I could have done is I could have actually taken my plot of Y high-res and T high-res and Y high-res. All right. But then let's just say this time I'm going to grab, say, about 15 values out of there. All right. So I'm going to all right. So just as a reminder here, so when we look at my high-res values, I got 629 high-res values. So if I wanted 16 of those, I'm going to take 629 or 15 of those, 15 or 16 of them. my step will be 41. Let's call it 42. So I'm going to do a step of 42. All right. And so what I'm going to do now is I'm going to plot T underscore high res, and I'm going to go from the first element to, and I'm going to step by 41 to the end of it. So this is going to grab out, let's just do it before we plot it. Okay, this is going to plot out 16 values from 0 to 6.15. So it's going to pull out 16 values that are stepped 41, 0.41, 0.82, and so on. So it's pulling out those values. So it's indexing into the t vector. So notice here, t1, of course, is 0, or t should do the high res. T high res, the very first index in t high res is 0. The 42nd value, okay, the 42nd value, because this was the first value, so we go 41 more values, so it's the 42nd value out of the high res vector is 0.41. And then the 84th value, is 0.82. Okay. It's actually the 83rd value, because we went, let's see, we went the first value, and then we go 41 more, so 41 more is the 42nd value, but then we go 41 more, okay, so we go 41 more is going to be 41 plus 42 is 83. So this is the 83rd value there, and that's where that comes from. So now we can plot those, so I'm going to plot those. And so it's going to be t underscore high res and 1:41:end, and then I'm going to plot the sine high res, which is going to be 1:41:end. Notice that you got to have the exact same number of values. So remember that my t high res and my y sine underscore high res are both the exact same number of elements. And so when I put this index rating in here, again, it's going to pull me the exact same index values out of there. And so now I'm going to plot a different marker here. I'm going to do a plus. I'm going to do a plus sign here for the marker, and I'm going to make that, I don't know, green. Okay. And then what I'm going to do is, so what I'm going to do is I'm going to set the marker size on these to be 10. Okay, so just to add an extra thing to make them larger. Okay, so you can see there, I guess 10 wasn't real large. Let's make it 20. And so we can see, you can see those plus sizes, you can see how large they are, but you can see how they're spaced along there. So these are just some different ways that we can work with the various elements within a vector. So you can pull out multiple elements at a time. Another option, another thing that we might want to do is, let's say, let's find let's get the index to all the values of y underscore sine high res. So we're going to use the find command to find the indexes where all the values of the high res, of the sine high res, is greater than, say, 0.5. Alright, so I'm going to get these indexes. Now using these indexes, I'm going to plot t comma high res at these index values, and y comma high res, sine high res, at these index values, and I'm going to plot these in red. So I'm going to plot these in red dots. And so what it's going to do, before I hit enter here, let's look here, and you see that the blue line, right, the blue line goes all the way along the sine function. But now what I'm going to do is anywhere where it's above 0.5, I'm going to make that red. So it's going to plot points. Now those points should be, there might be a little bit bigger than the line is now. And so when I run that, I'm going to get red lines. I'm going to get red points all along here. So it highlighted in red, essentially, the part of the sine wave that was larger than the 0.5. So anywhere where the sine wave went above the value of 0.5, I plotted that red. Now the other thing is we could use this index now to find those points and plot a dotted line. So remember, to plot a straight line, you need 2 points. So what I'm going to do is I'm going to take this first point where the sine wave first crosses 0.5. That's going to be my first point. So at whatever time vector that is, which I'm not quite sure, just by looking at it I can't tell, and whatever the y value is. So what I'm going to do is I'm going to take this index here. So I'm going to look at my index. So the first value of my index is 54, and the last value of my index is 262. So what I'm going to do is I'm going to plot a point. I'm going to plot a point where t, I'm going to plot 2 points. I want where t is index 54, which is the first value in the index. Okay. But it needs to be from the high res vector. Okay. And then I'm going to plot t of the last value, right, which is at time 2.61. Okay, so that's, you see 2.6 is right about here, and that's where the red ends. All right, and so what I'm going to do is I want to print a horizontal line to kind of mark that. So I'm going to go like at the t high res from index end and index beginning and plot that point. So I'm going to plot a horizontal line starting at t high res 1. So that's the first point. That's the x, or the independent value of the first one, and this is the second point. So you plot the 2 t points, and then I'm going to plot the y values. And then I'm going to plot the y value there, sine high res, index end, and then I'm going to plot this as a black line. I'm missing a parenthesis here. Okay, so oh, I'm missing a square bracket is what I was missing. Okay. Alright, so that plotted a black line right there from the beginning of the red to the end of the red, a horizontal black line there. Now, the thing is that we ended it right there at those points where they started being red as they were following the sine curve. So, you know, when you're drawing a horizontal line like that, you may want to extend it a little bit. So I may want to like extend my index here minus 10 values. So that might be a little far, but it'll really highlight it. And then plus 10 after it. Okay, so, you know, this will just kind of make that horizontal line look like it's kind of cutting it a little bit. Plus 10. So we're going 10 elements before the index and then 10 elements after the index. Okay. For the time, but I don't want to do that for the y value. If I do that for the y value, it's not going to be in the right spot. Alright, so somewhere I lost a parenthesis again. End. I had my parenthesis in the wrong place. Index minus 10 parenthesis. Parenthesis. Now, another way I could do this, instead of doing the high res using those index values, because I know from my original sign, or my original find function, here was the find function. I was looking for anything greater than 0.5, so I could actually just go from 0.5 to 0.5 for those values. Okay, and so as you can see there, then that extended that line. But also notice that because I just made it that hard-coded 0.5 value, this was supposed to be plus 10. Alright, so notice the original line up there was actually the true y values, which were not exactly 0.5. So that was another point that I kind of wanted to illustrate here. Let me change the color of this line. Make that line blue. Alright, so that we can kind of see that there. And we'll zoom in on this a little bit. And so I wanted to illustrate to you here that where these lines, where the black line ended, was the true numerical value out of the sine function, where the blue line ends is exactly at 0.5, even though we don't have a true matching point of that. So this, look at that. So if we look at the y value at that first index point, it's not exactly 0.5, right? It's actually the value of it was 0.505, because remember the find command, I was asking get me something, anything and everything bigger than 0.5. Now I could have actually even said get me everything greater than or equal to 0.5. Alright, but chances are that that value is not going to change any, because the chance of performing a sine function and getting exactly 0.5000, right? This right here is saying give me anything greater than or equal to 0.500000. The chance of getting that exact value is very, very slim. So you know, you always want to do a greater than equal. If you're looking for exactly 0.5, right? If I tried to do the find command for exactly 0.5, I would use 2 equals. That would be exact, but the chance of finding something exact, okay, I'm getting this out of bound error because there is no exact value of y sine underscore high res of 0.5 exactly. Okay, the closest thing above it that we can find is 0.50553. So it's not an exact value. So when you're using the find command, you usually either want to use a greater or greater than or equal to. The chance of finding it exactly equal, unless you know for fact that they're integer values, you're not going to find a true exact. It's just going to be something close to that. So keep that in mind when you're working with the find command. But again, the find command allows us to pull out these indexes so we can pull out sections out of long vectors. Because when you're talking about vectors that are hundreds or thousands or even millions of elements long, you can't do you just can't do too many. Now another thing here, notice remember the resolution of a typical screen is about like a high def screen is 1900 pixels from left to right. And notice the graph doesn't start right at the very edge. So there's like a couple of there's like 150 pixels right in here. So when I plotted this to get a smooth line, I used 629 elements. Now if I created a time, I'm going to clear my figure. Alright, so my figure's still there, but there's nothing in it now. But I just kind of want to illustrate here. I'm going to create a brand new time vector starting from 1, and I'm going to step 0.001 times 2 times pi. Now when I do something so big, I'm not going to put the semicolon here, and watch what happens. This thing is just running and running and running and running. Maybe I shouldn't have done this because I don't know when this thing's going to stop. I've got so many. So notice now I've got 62,000 of these elements. 62,000, right? Whose T is 62,000 elements. Now, when you're doing simulations, you may need a time step that small, and you may need to create a vector of 62,000 elements. And so that now when I do my sign, I'm going to say y underscore sign is equal to the sine of t. I'm going to put the semicolon this time because I don't want to sit there and watch all those numbers. So now we have t and y. Y underscore sign. And both of them are 62,832 elements. So now if I try to plot these, especially if I try to plot them with like markers, what did it do here? Plot t underscore sign. All right. It plotted that okay. Let's recall my t one more time. Let's add 2 more zeros. Oh, that was a mistake. I forgot that semicolon. Okay, so man, this is going to run for a very long time. So because now we're doing 6 million of these. Okay, so you definitely want to put that in there. I'm going to pause this while finishing. Okay, so I didn't put my semicolon there, and this thing is running. You can see it's up to about 1 million now, and it's still running here. I had you on pause for a little bit because I didn't want to waste too much time. I'm going to pause it again here till this finishes. All right. Alright, so I didn't put that semicolon there, and this thing has just been running. I've had you paused a couple of times now, and it's still running. The reason it's taking so long is that it's trying to display millions of numbers, and so it's actually the display of these numbers that takes so long. If you actually are to create the numbers, your computer can do that extremely fast. The slow part is trying to display it on the actual display, and so especially as these vectors get longer, you definitely want to remember, put that semicolon there so that it will create it. And I mean, it may take a little while to create it when you're creating literally 6 million or however many I'm creating there, but it can create it in, in a fraction of the time that it takes to actually dump it out to the screen. So that's what we're kind of waiting for. I'm just going to go ahead and close out Octave and restart it, and then I'll restart the video here. Alright, so I've restarted Octave. One thing I wanted to kind of point out to you here is that this command history window shows you the last few commands that you've actually executed. And so you can kind of see what I just created my figure again, and then cleared out everything, cleared the commands, but you can see those down there. I don't really find this real useful, because remember, you can recall your commands using the up arrow keys, number one, and number two, if you just want to see them, you can always just type history, and you can see not only the commands that I ran before, but commands that I had been running previously. So even in a different session. Now, because I ended up killing the session that was running so long because I forgot to put that semicolon and I got tired of waiting for it, it did not actually save anything that I was doing at the early part of this video. But so what we're seeing is commands from some previous exercises here. Okay. But so let's go ahead again. I was creating a t vector, and I'm just going to create a lot of values here. All right, and I'm going to 2 times pi, but I'm going to remember to put my semicolon this time. And so you notice there now it created this t vector with 6 million, over 6 million elements in this t vector. Okay, so there's over 6 million. I think last time I must have had my t vector slightly smaller, or my time step slightly smaller. So now I think this is actually what I was doing. So now notice how quick that was. See, I didn't have to wait and wait and wait and wait and end up, killing it, because I put the semicolon there. So it created, now it's got over 62 million elements in this t vector. So then I can create my y vector, y underscore sign is equal to the sign using this t vector. Now this is going to execute the sign function 62 million plus times. So it took it, a half a second there to do that. But, now when we see this, right, both of these are over 62 million elements long. And now, if I try to plot these, okay, I might have to stop this again, because if I try to plot this, I'm going to run into the same kind of issue. My figure is already created, but when I try to plot this, it's going to try to plot 62 million points. It actually did it fairly quickly on my computer, actually faster than I thought it was. But my kind of point here is the fact that, again, you really don't need 62 million points in a plot. 6,000 points in a plot would be way more than enough. So, if you take and get the length of your vectors, and let's say that I want, so I only want like 6,000 of these. Okay, so we can take this and since I've got 62 million, right, I got 62 million of these, and I only want about 6,000. I'm going to divide by, say, let's just say I'm going to divide by this length by 1,000, right, would give me 62,000. Or if I divide by 10,000, I would get 6,000. So if I wanted to plot like 6,000 of these, I would do the plot, Okay, so now I would do the plot, and now the t-vector, I'm not going to change the t-vector, but I'm only going to plot from 1 to 10,000. I'm going to do steps of 10,000, and then to the end of that, and then I'm going to do the same for the y. All right, and remember, you can highlight. I don't know if this works on Windows, but on like when you're on the OSC computer, for instance, you can simply highlight and then middle click and paste those values. All right, but so now when I do these plots here, these plots are only 6,000 points instead of 6 million points. All right, so there's honestly in a plot, you know, even though you may have to, when you do your simulation, you may need 62 million points in your simulation, because we'll talk about that later next week when we get into modeling and stuff. But that time step, if the time step is too big, the simulation can go unstable, even though the system may be stable. The problem is that you're skipping ahead in time too fast if your time step is too big. So you may need a simulation with 62 million calculations, but you don't need to plot all 62 million of them. And on some systems, you may notice, like if you try to plot these 62 million points on your system, especially a Windows system, it may actually take 10 minutes or more to plot it, because it's trying to plot 62 million points when honestly you don't need 62 million points on the plot. So using this index notation, you can strip it out here so that, you know, if we look at this, so t let's call this like t points here. Alright, so my original t-vector is 62 million points, but the ones in the plot, there's only 6,284 points in the actual plot. Okay, so always keep that in mind there. You know, if your vectors get too huge and you try to plot those, you may be waiting a long time for that to plot. Just like when I forgot to put my semicolon, I was waiting a long time because it was dumping out those numbers and numbers and numbers. I mean, the computer can do the calculations and stuff really fast, but when it's trying to display millions of points, it's going to take a while to send it out to the display. And it's not actually your video card that's the issue, but it's trying to generate the plot that's the issue. And so just sending that data out takes a long time. And so you need to make sure, like when you do the plots, that you kind of sample. So basically that's the term I should have been using. I'm sampling this. So I'm sampling it, and I'm only plotting every 10,000th point out of this. So I got a 62 million points, and I'm skipping 10,000 points, or 9,999 points, and I'm plotting the 10,000th point. Every 10,000th point I'm plotting. And so I'm only, out of over 62 million points, I'm only plotting 6,284 points. So keep these things in mind as you're working with these vectors and you start performing your simulations.